Thank you very much for your kind invitation. As an Irishman, I have a great deal of difficulty compressing information. So when I was preparing this talk, I started off with a Columbia Presidential Scholars Talk, and that was about an hour. Then I got a shortened version of the Columbia Presidential Scholars Talk, and then I got a short version, and then about midnight last night I got an even shorter version, which I'm not sure I'm going to make my 15-minute schedule. I had thought that I would provide you with a menu of the topics of this topic, the laws that bind us, laws, mechanisms, and then I thought that would take too much time also, so I'm just going to dive in. Right. New laws to be expected in the organism. This is Erwin Schrödinger, who wrote this book. Pardon? Oh dear, I hate microphones. Oh my goodness. Yeah. Okay, so now here's my entry point, a very fast entry point. Schrödinger had a very interesting life in Dublin, by the way. That's where he wrote this book. But this is his chapter 7, and the title is New Laws to be Expected in the Organism. And given the title of our symposium here, our seminar, we would say also New Laws to be Expected in Organisms. Isaac Newton, actually, even earlier, is often said about Newton that he was concerned that the only thing that mattered was motion. But here is a quote from this very nice book. The power of life and will by which animals move their bodies with great and lasting force demonstrate that there has to be other undiscovered laws of motion. Huh? Newton, eh? So where did the physics go with the animate motion? Yeah, interesting question. Why is this? I have to go into this each time. Okay. So 1. New laws to be expected in the organism. What are the new laws of? The new laws are of coordination. And this is a quote by Howard Petit, an eminent theoretical biologist. I do not see any way to avoid the problem of coordination and still understand the physical basis of life. Petit was writing this at the time when people like Delbruck were saying that the problem of life was solved. We know all the steps, and Petit said, well, how are the steps coordinated? You see? And here was the problem, and this is the problem that I'm going to address here briefly. Unlike the laws, so this is a stipulation here, if you like. Unlike the laws of mechanics for inanimate motion, the new laws of coordination specify the flow of coordination states produced by functional synergies or coordinative structures. That's the mantra. The flow of coordination states produced by functional synergies or coordinative structures. I'm not going to tell you very much about coordinative structures, but in this theory, they are the basic unit of living systems, not circuits or anything like that. They have to handle variability of structure, they have to handle multifunctionality, they have to handle degeneracy, and this concept is empirically and theoretically the concept that I think we need. What's new about the new laws? This is something I'm working on a little bit at the moment myself. The coordination states here, which have to be found, remember, in biology, are defined in terms of collective variables. Okay? So I'm going to illustrate the notion of collective variables here in a second. A collective variable, what is a collective variable? A collective variable is a low-dimensional description of a complex system. It's relational. It's a relational idea. It enfolds or entangles or spans neural and mechanical parts and processes, including the typical distinctions we make, say, between sensory and motor, or cognitive and motor, brain and body. So it transcends those kinds of things, and in the process eliminates arbitrary divisions between things, which I would say is something that we always do as scientists. but that's not necessarily the way nature does it. So the coordination dynamics here, it deals with coordination states which are functional and context dependent. So here's an example. This is Michaela Wallace, my goddaughter, who was the, so since I'm in New York, I have to talk about ballet. Just before her retirement, she was 10 years as the principal ballerina at the BC Ballet in Vancouver. I thought, let's have a look at how she does it. So we brought her into the laboratory, and that's her Vitruvian self, Vitruvian woman, yeah. And there are 32 sensors in 3 dimensions. That's a 96-dimensional space. Okay, pretty complicated, complex. How does she do it? Oh, yeah. This is called structure of emotion. I get emotional watching this. So this was her own choice. She choreographed, this was her own piece of choreography. This is the way she wanted to do it. And then, of course, as experimentalists, we say, well, could you do it a little bit faster or slower? Or could you do the same dance using different emotions? Okay? So let's look at the relationship between emotion and motion. So let me see, I think I can. So this is one of the emotions she's trying to express. What do you think it is? Fear. So the middle one is her doing it normally. And in this case, we've centered the motion around the center of mass so you can see it. So she's in a fixed coordinate frame. Anyway. So we analyze this using something called principal components analysis. We have time series of the legs and arms. As I said, it's 96-dimensional. You have a correlation matrix. It's symmetric matrix. You calculate the eigenvalues and eigenvectors of the matrix. The eigenvectors are the patterns. The eigenvalues tell you how much variance is accommodated by each pattern. And then you can reconstruct the motion. And then when you do that, actually you see that see if I can do, yeah. So these are the patterns. These are the principal eigenvalues. And these are just the top 4. And they're accommodating about 80 to 90% of the variance. That's each pattern and its temporal dependence that you see here. So the time series is the temporal dependence of each pattern. And the lambdas are the eigenvalues. So the whole thing can be reduced to this set of basic patterns. And in fact, if you ask the question, what are the basic building blocks of coordinated activity, such as the way you perform a dance? In phase and anti-phase in 3 different directions. That's it. Okay? In phase and anti-phase in 3 different directions. Boom, boom, boom. That's it. Remarkable aspect of the coordination in complex biological systems of high dimensionality is that they live in this space of low-dimensional, context-specific patterns, which we call coordinative structures. Okay. What's new about the new laws? One more. Coordination states are defined in terms of collective variables which wipe out the distinction between separate things, parts and processes. That's a very dramatic claim. Here's some experiments we're doing at the moment. This is a baby. Just watch the baby, I'll just talk. The baby's about 4 months, and as you can see, she's again got sensors on. And this is a mobile that's on top that she's looking at, and it's quite attractive. But if you tie a ribbon to the baby's foot, and the ribbon then triggers the mobile, you see what the baby likes to do. The baby likes to move the mobile. Is that 10 minutes for me, or am I? I'm at 10 minutes. Very good. And then, of course, you can decouple. So the baby's uncoupled, then it's coupled with the ribbon, and the ribbon causes the world to change. Yeah? We think this is the origins of agency. It's a well-defined system that can be nicely theoretically understood. So I've done this here, as you can see. I like to be able, is there a pointer? I don't know. Yeah. So the collective variable signals this shift from meaningless to meaningful. So here's the foot in the mobile. These are the trajectories of the foot. This is an idealization. And this is the relative phase between the foot and the mobile. And you can see there's no particular phase relation. But then at a certain point, the baby realizes, this is me. I am doing this. And then the baby controls the mobile. Yeah? And it's actually autocatalytic. The mechanism is autocatalytic. The baby moves the mobile is attracted to the baby. So it's a circular loop. It's a beautiful thing. The new laws, right, specify the flow of coordination states produced by these coordinative structures and are expressed in the language of informationally coupled dynamical systems. It's a theoretical statement. Great deal of empirical evidence, for example, from phase transitions in coordinated movement, through bimanual coordination, intralimb, arm, leg, between people coordination. You can see the same phenomena that are observed in all these cases. Typically, there are only a few basic patterns, and they shift from one pattern to the other. And when they do, you see these characteristic features of so-called non-equilibrium phase transitions. Critical fluctuations and critical slowing down have been seen in all of these dyadic situations. And this is the extended HKB model that handles all those. The person on the right is Hermann Haken, the father of laser theory. And HKB is probably well known, but this is the key aspect here for social coordination is that there's the parameter. Oh, sorry, let me go back. Yeah. So the key aspect here is this phi dot is the collective variable, how it changes in time. That's a function of two factors, principal factors. One, the differences between the individuals, right? And two, the coupling between the individuals. That's it. Differences between us and the coupling between us. Those are the two cooperative, competitive aspects. And what you see here is actually the flow of the dynamics in this very simple example. You do this by plotting phi dot against phi. This shows you these black dots are where the function crosses the ordinate, and the black dots are the stable states, and you can see there's multiple stable states. Then if you change parameters, you get transitions, multi-stability, and then you get this very interesting metastable regime, where there are no longer any coordinated states at all, but simply a tendency for the system to live where the coordinated states used to be. It's a very flexible, non-noisy process, a deterministic process. That's to say there are two competing processes that form the coordination. How brains and people couple, I can only say a few words about this. Now, many experiments, here you see, these are the so-called phi complexes. These effects occur when people are coordinating together, typically. And they occur in different frequency ranges. What you see here is alpha, beta, gamma. This is the so-called phi complex discovered by Tognoli et al. You can do all the brain imaging in this between two brains. The mechanism now that people are focusing on very strongly is this notion of metastable phase attraction between neural ensembles over multiple frequency bands. That's the key thought. And very quickly, this is an old quote from Francis Crick. The discovery that the brain was run phasically would probably constitute a major breakthrough. He wasn't quite right. Of course, there are many brain rhythms associated with all kinds of things. The brain is a geography of improvised rhythms. And you can see them at multiple scales. Here you see where these rhythms are phase coupled, These are different systems at different levels of description. Here's where they're uncoupled, so there's no particular phase locking. And here's this interesting metastable regime where there's a tendency to coordinate, then you leave, you dwell. It's a dwell-escape dynamic. It's a convergent, divergent dynamic. So coordination entails and explains metastability. Metastability, as this quote goes, is an entirely new conception of brain functioning where the individual parts of the brain exhibit tendencies to function autonomously at the same time as they exhibit tendencies for coordinated activity. And this is definitely also seen in social brains. This is the last part, and I'm nearly at the end, and so I'm not going to be able to tell you very much about this. Last but not least, the recent work with Mengxing Zhang reconciles the Kuramoto equations. I'll show you, I won't show you the equations, but I'll show you what they explain, that were also developed with Art Winfrey and Stephen Strogatz with the extended HKB. So Kuramoto deals with n-dimensional, actually infinite dimensional systems. HKB deals typically with coupled dynamical systems. And the question is, how do you get from the many to the few, or the few to the many? And we did experiments with 8 people. And I can't tell you very much about these experiments except to say that the key manipulation is that people move at different frequencies. They see their own movements and they see the motions of the others. Actually, it's a human firefly experiment that Julia mentioned. It's exactly what we call it. So Kuramoto, I don't know if people know about this, but actually Kuramoto wrote his book at Hawkins Institute 3 weeks before I arrived there in 1984. And his equation is used for neural network synchronization, functional connectivity, chemical oscillation, whole range of phenomena that deal with coordination, social and otherwise, are handled by the Kuramoto equations. Here is us working with the extended HKB that has also a lot of data that have been accounted for, and I mentioned some of that. And the question was, how do you get the two together? This is very nice. This was published some years ago in Nature, where people studied the onset of clapping in an audience. Actually, I saw a very nice example of this in the Game of Thrones, where Khaleesi says to the Unsullied, that the slave, she said, you are free. Will you join me? And they're all there. There's 8,000 of them, and they've got a spear, and one taps. Boom, boom. And that just starts a collective boom, 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 boom. They all tap together. And this would be perfectly explained by the Kuramoto. At a critical value, they all go into group synchrony, and this is going to lead into Carolyn Palmer's talk, I hope, and end mine. I'm showing you here the classical Kuramoto model, when you analyze the data, has only got the onset of synchrony, 0 phase. And here we're manipulating the delta frequency, the frequency difference between the components, as we did in the experiments. So here, this is what's going from left to right. Here are the same components, changed by 3.3 hertz, changed by 0.6 hertz. And you see that the in-phase, 0 phase locking sort of diminishes as you make the components more divergent. Human behavior, however, when you study it in these small groups, has both anti-phase and in-phase, which disappears eventually when the components are too different from each other. And this is our computer simulations and analysis, by the way, of the behavior, which, as you can see, has the anti-phase state in it as the human behavior displays the data as well, which disappears eventually as the components become more different. That's from left to right. So this is where I will leave you. The in-between, what shall we call it? This is actually the equation. The followers of Kuramoto stress incoherent to coherent synchronization. The followers of HKB have bi or multi-stability, order transitions, metastability. These are essential features of extended HKB. The middle ground experiment shows that these features are crucial aspects of the coordination dynamics. Therefore, the middle ground in between is captured fully by this generalized HKB model. As Robert Frost said, the secret sits in the middle. We dance round in a ring and suppose, but the secret sits in the middle and knows, yeah. I could leave it right there. I think, maybe, was there something else? Yes, there was. The laws that bind us reconcile the inanimate and the animate, the many, the few, and the in-between, the spontaneous, the baby's spontaneous kicking that becomes agent-like, and the directed intentional aspects of complex living things. I thank you for your attention, and I would like to say that most of this work is due to my wonderful colleagues. Thank you.